Good morning, good afternoon, good evening, everybody. Welcome to the EMinars for 2023. Today we have Gesa Franz talking, but before I talk a little bit about her and what she's going to present, we'll do the usual introduction. If you can go to the next slide, Alan. So most of you will probably have seen this page because you registered through it, but if you haven't, all the past and future planned EMinars can be found on MTNet. There's a link on the main page if you can't remember the URL here. There you can register for upcoming EMinars, and you can also see YouTube videos and get the PPTs from previous speakers if they have permitted us to put those online, but I think the vast majority of speakers have done that. So there's now, well, we are in our third year, 2.5 years of previous presentations. Next slide, please. So for the next few weeks, we have some exciting EMinars, but also a couple of free spots. So next week, we have Richard Smith on the geophysical contribution to the Metal Earth project. Then we have a free slot on the 8th of February. So if anybody here has something interesting to talk about, then please get in touch with either Alan, me, Stefan, or Kate. On the 15th of February, we have Brian James on the interferographic TEM method, array beamforming for resolution improvement. And again, on the 22nd, we have a free slot. So please get in touch with us. And next slide. Yeah, and today we have Gesa Franz. She will talk about integrated geophysical analysis of passive continental margins, insight into the crustal structure of the Namibian margin from magnetotelluric gravity and seismic data. And Gesa is a PhD student who just handed in her thesis at GeoMar in Kiel, and before that she did a master's there on a similar subject, so very related, and has been involved in various cruises and acquiring data. And actually, this is something that I've been involved in as a sort of co-supervisory function. So I'm very happy to present Gesa, and well, I'll hand over to you.
Thank you, Max. I'll start sharing my screen. Okay, can you see that all right?
Yes, that looks good.
So thank you for the introduction. And also thank you to Max and Alan and the others for organizing the seminar and giving me the opportunity to present here. I'll go along. So we are talking about passive continental margins, which are the tectonically inactive transition between continental and oceanic crust. And we usually differentiate between two end member types, the volcanic and the non-volcanic passive margin. And here on this lower map, you see a distribution all around the Atlantic Ocean, Indian Ocean, around Australia and the coast of Antarctica. And on the right-hand side, you see sketches of the archetypical structures of these non-volcanic margin at the top and a volcanic margin at the bottom with the typical related features. And these are on the non-volcanic margin, usually an abundance of crustal faults and very deep crustal faults at some point that eventually reach all the way to the Moho, which are all due to massive continental stretching. And at some point, these deep falls make way for mantle accumulation and then also possible serpentinization of the mantle. And at the bottom, you see the volcanic passive margin, which is usually characterized by a narrow rift zone because it's then followed by the arrival of magmatism. And their typically related features are continental flood basalts, which are not imaged here because they would be further onshore. And then surface flows, which are here called these SDRs, so seaward dipping reflectors. That's a seismic attribute. In the lower crust, we have some magmatic underplating, and then generally thickened oceanic crust and possibly a lot of intrusions into the crust. And what we are focusing on, or what I was focusing on in the last years, is the Namibian passive continental margin, which is located at the northern coast of Namibia. And here on this little map inlay, you can also see a very prominent topographic high, which is in the middle of our survey area, which is called the Walvis Ridge. And that is a hotspot track that connects the Namibian coast all the way to the Tristan da Cunha hotspot at the Mid-Atlantic Ridge. The breakup of the South Atlantic Ocean is dated to be successively happening from south to the north, and at Namibia, it's dated at around 133 million years ago. The Namibian passive continental margin has been a focus of research for a long time, which you can see on this map. There's a lot of structures imaged from geophysical and geological studies. And here you can see some of the observed structures. And that also motivated this German Research Foundation project Sample, which was running from 2008 to 2017, where among others, it was the data that I was using was collected. So there's MT data along these two profiles, and also seismic data acquired at the same time. So that was all yielded at an integrated data analysis. So within this project, as I said, there were some great and large data sets acquired, and it gave me the opportunity to perform this work. And my work focused on the one hand, improving the geophysical models, especially the resistivity model, through integrated analysis and also through joint inversion. And within that, compare different methods or different approaches of joint inversion. And then on the other hand, linking these geophysical results with actual geological interpretations concerning the margin formation history and large-scale geodynamic processes. And in a very general matter, the passive margin research is also motivated to understand better geodynamic processes and also plate tectonics. And in that context, the formation of large volcanic provinces, because in the larger picture, these large volcanic provinces are inherently related to a carbon cycle, and with that to the broad and up-to-date topics of global warming, mass extinction, or ocean acidification. So to follow these overarching objectives, my talk will focus on two main parts. The first one focuses on the inversions and on the comparison of the possible model improvements that we reached. And then the second part will be linking these geophysical results to geological interpretations. And for that, we performed a user-unbiased parameter analysis using parameter clustering. So this is the first part, focusing on the inversion results, and all of these results are also published in a JGR paper. First, I quickly introduce the data that we used. So here you see a map of the outline of the MT data. So that's 32 marine MT stations, and then an additional 8 onshore MT stations, and all of these were deployed in 2010 and 2011. And as you can see, the survey was originally planned along 2D profiles. The analysis of the data showed that it has a 3D character. So we ended up performing 3D inversions. And we did that on rectilinear grid with 10-kilometer horizontal cell size, and then increasing vertical cell size to match the increasing sensitivity of the MT data. And the starting model that we're using for all of the inversions includes the bathymetry, a sediment layer, and then a 50-meter half space. The second data set is actually a model that I want to present to you. It's a large 3D geological model published in Maestrenko et al. And it results from gravity modeling and also includes some seismic constraints. And this model is made of larger blocks or layers of distinct density, and some of the important features that includes some deeper sedimentary basins, distinct difference between the oceanic crust and the continental crust, then varying Moho topography, as you can see here, and also in these pink colors, several lower crustal high density bodies. And the last data set I want to present here is a satellite gravity data set, and I will spend a little bit more time on that because maybe a lot of you are a little bit less familiar with gravity data than EM data. So I'll explain some of the corrections that we performed there. The gravity data that we started with is the eigen anomaly that is available from the ICGEM online services. And I used a spherical approximation of this at 3,000 meter height. And this we have to do because in order to use it as a constraint in joint inversion, we have to apply some corrections, and we want to calculate these corrections above any of the affecting masses. So the corrections that we're applying, you can see here at the top picture, the A, this is the anomaly that we get, this eigen anomaly, which is basically a free air anomaly. And you see that is very strongly influenced by the topography. So the anomalies kind of follow the topographic lines. Here in red, you would see the Walvis Ridge, and then onshore, you can also see some mountain ranges. And this is not really what we want. We want to see the density variations within the crust. So the first thing we do is a topographic correction. And we did that by calculating the effect of a mass deficit in the ocean. Right here is a small sketch of this, and the extra mass that is coming from onshore mountains. So we simply set up this model here and calculate the gravity effect, which you see on the right side, and subtract them from each other. And then what we get is equivalent to the Bouguer anomaly here in figure C. And if you look at it first, that looks even less interesting than the figure A. And that is because it is the Bouguer anomaly is usually very strongly influenced by the density contrast at the Moho. So it also images Moho topography, and that varies drastically between oceanic and continental crust. So we're doing another correction, the isostatic correction, where we have a similar effect of where the crust is deeper than a reference depth. We have a deficit of mass, and where the Moho is shallower, we have an extra mass, and we calculate again the gravity effect and subtract it. And then we finally get to this anomaly here in E, which is our inversion input, and that emphasizes crustal anomalies between the topography and the Moho. And then the second part for the gravity inversion, what we have to do is to create a proper starting model, because gravity data usually has little depth resolution and therefore usually needs either a better starting model or some additional depth constraints, for example, from seismics. So what we did here to create the starting model is we take that structural model that I presented 3 slides ago from Maestrenko et al. And transformed it. And we transformed it because the input data we're using are gravity anomalies. So our model also needs to be an anomaly, density anomaly model. So we just subtract sort of a 1D Earth reference model, which is shown here at the bottom left, just consisting of an air layer, crust, and mantle. And then we also need to apply these corrections that we applied to the data. So both of them together yield this model that we subtracted. And with that, we have a density anomaly model that we can use as an input, as a starting model. And here on the right-hand side, you just see a forward calculation at the bottom of this starting model compared to the input data. And we see that we already have kind of the large-scale anomalies, like this big positive anomaly at the landfall of Walvis Ridge, and then negative anomaly here in the deeper sediment basins or in the oceanic domains. And all of these data sets, these 3 data sets that I presented, we then combined in different joint inversions or in different inversions. And the first one is obviously an empty only inversion, just to have some sort of reference. What are we actually trying to improve? The second inversion is then a constrained inversion of the MT data with using this density model by Maestrenko as a structural constraint. And using this, the constraint was implemented by cross gradient coupling. So with that term phi cross here. And that actually, the cross gradients are from an idea from Gallardo and Max Méjou, and they're made up of these cross gradients, which are the cross products of 2 different models' spatial gradients. And I usually always find this image by Max really helpful to visualize the concept. So you take the gradients of 2 different structurally different models. So in red here, we see the gradients of model 2, and in black, we see the gradients of model 1. And then if you take the cross product of these 2 gradients, that's the cross gradient that you get. And you will see that this is 0 wherever one of the model's gradients is 0, and also where the both gradients go in the same direction, as you see here in the upper corners. And then everywhere else it enforces a constraint where the 2 models are structurally different. And last inversion that we performed was an actual joint inversion of the satellite gravity data and the MT data. So there the objective function also includes terms for the gravity data and density model regularization, basically. Okay, now just quickly, here's some results for the data fit. So this slide shows some pseudo sections of the apparent resistivity. So that's for every of the MT stations and every period. I know there's a complex figure with a lot of information in there. I just want to point out a few things to you. The first thing that is well, lucky or good also is that all the inversion approaches have similar MT data fits, and all of them are able to recover the large scale anomalies. And that includes some low apparent resistivities here in the short periods that are recovered by all of the inversion approaches, and then some very high apparent resistivities here in the longer periods that are also recovered mostly by the inversions. Well, just here you see that they're not always recovered to the same extent. And another thing that I want to point out, that it seems in general that the onshore stations are a bit harder to fit here for us. And now with that data fit in mind, we come to the interesting part, actually comparing the models. So how did the constraints that we used actually affect the models? And here you will always see on the left side the resistivity models, and then on the right side the density or density anomaly model. And we are looking at the 2 profiles because they're we obviously have the strongest constraint very close to the data. So first we're looking at this coast parallel profile. And also there I will point out a few observations that we have. So first of all the models have the same or similar large scale anomalies, which is for ones this large resistor R. That also comes together with high density and it is also in accordance with imaged high velocity models below Walvis Ridge. And then the second feature is this shallower conductors here, C3, which are accompanied by thicker sediments, but the conductors reach a lot deeper than the imaged sediment thicknesses. And the last prominent feature is this vertical conductor C1, which coincides with the crustal fracture zone. However, that fracture zone would not justify the extreme depth of this conductor. So after some model tests, we also were able to conclude that this is probably an artifact, the extreme extent of this conductor. There might be an effect in the upper crust from a fracture zone, but it shouldn't reach down to 80 kilometers or even more. And if we look at the differences between the different joint inversions, what we see is especially that this model constrained inversion, the JI1, has some kind of horizontal lines that are imprinted around the Moho here especially. However, we also see that this line is not really completely enforced in the model. So the resistivities are still high below this Moho, and that kind of proved to us that we need higher resistivities in the mantle as well. And also it here with this weird conductor, this artifact conductor that I talked about, the density constraint helps to decouple it from the upper conductor. So that gave us basically the hint to test for this feature if it's really needed or if it might be an artifact. Unfortunately, it's not, it somehow wasn't able to completely remove this artifact. And then let's look at the second profile, which is the coast perpendicular profile. And here it's a very similar picture. We see the same large scale features, this large resistor R all along the Walvis Ridge. And we see some shallower conductor C2, which is as along the other profile, it coincides with sedimentary basins, but it's still a lot deeper than the imaged sediments. And again, we see some horizontal lines that are imprinted into the resistivity model through the density constraint at Moho depth. And also we see it here in this shallower conductor that we also have a horizontal line that's imprinted. However, there is still a conductor below that line. So again, that gave us a idea, or that emphasized that we actually need conductive features below the imaged sediment thickness. And after we looked at the models and looked at some of the comparisons, now we could look, go to the second part where we link these geophysical results to geological interpretations. And we performed a unbiased parameter analysis for this with some automated clustering. And these results are presented in a manuscript, which is currently under review at the EGU journal Solid Earth. Just very quickly here, the input models. That's the models from the actual joint data inversion, so from the gravity data and the MT data. So we have a resistivity model and we have a density model. And for the better comparability with other data, we also used absolute density values here. So what's imaged, although the inversion input is a density anomaly. So you see that we just add the reference model here, which gives a very strong contrast already at the Moho. And that led us to separate the different domains in the clustering. So we just cluster all the parameter relationships above the Moho and then below the Moho. And after some testing, you will see that in the next slide, we also separated another domain, and that's the sediment domain, which we defined based on seismic reflection data along the profiles. And one last thing, so we have this large 3D model the outline I showed you earlier on a map, but for this clustering, we only used the model cells, which are in a horizontal distance of maximum 10 kilometers to the MT stations. So that's where we believe that our model is definitely well constrained. And then we took these two parameter models and performed a Gaussian mixture model clustering, where the clusters are generated from Gaussian distributions. And then they typically have an ellipsoidal shape, as you can see here in an exemplary image. A nice thing with Gaussian mixture modeling is that the clusters can overlap, because in the GMM, every data point is actually assigned a probability with which it belongs to each of the clusters. So for example, if you have a point here in between the clusters, it is assigned. If you take this red point, it is assigned to the bottom cluster, but you see that the probability is almost similar, that it belongs to either of the clusters. So that's a great measure for the certainty of the clustering. And as a last point here, the algorithm needs the input of the clusters. So for each of the domains, at the set, sediment, crust, and mantle domain, we defined the number of clusters earlier, and therefore we took two theoretical information criteria, which are the archaic and Bayesian information criteria, which maximize the likelihood function and therefore data fit, while minimizing the number of clusters. So we just use the elbow method here to define the number of clusters in each domain. And these are the defined clusters in the three domains. You can see we have 2 here in the sediment domain, and then we have 4 to 5 in the crustal domain, and another 4 in the mantle domain. On the y-axis here, you see electrical resistivity, and on the x-axis density. And also with the transparency of the symbols, we show the probability with which they belong to their cluster. So that's a measure for uncertainty. And the fully saturated symbols here have a probability above 90%. The transparent symbols have a probability of 60 to 90%. And then if you see some dots without color, that means they have a probability less than 60%. And especially in the intersection of clusters, for example, here, also here in between, we have larger uncertainties. But we'll now look into each of these separately, step by step. So the first one is the sediment domain. Here you can see again the clustering, and then I will always show you the 2 perpendicular MT profiles with the distribution where the clusters are along this profile. And we have 2 clusters in the sediment domain. They are very clearly separated as one of low resistivity below 30 ohm meter and also low density below 2,700 kilogram per cubic meter. And they are distributed along Walvis Ridge, mostly near to the coast, and then all along in the south of Walvis Ridge, here along parallel to the coast. And then we have a second sediment cluster, set B, which is the higher resistivity and higher density cluster. And this is located further offshore along profile 100, so around this domain, and also in the very north, so here in the deeper basin north of Walvis Ridge. The second domain here is the crustal domain that we look at. And so there's a little bit of a specialty why I said 4 to 5 clusters, because the clustering itself indicated 4 clusters. And after some testing and seeing where these clusters belong and how the probabilities are, we actually decided to manually divide this cluster at 400 ohm meters. So that's these dark green triangles and then the lighter green squares. By the automatic clustering, this was 1, and we kind of manually separated them because it gave us clearer interpretations. I'm not going to go through all of these clusters. I'll just point out the 2 most important. And this is one, the very low resistivity and low density that's below 50 ohms mostly. Crew A right here, the yellow stars. And these are similar to the sediment layer close to the coast along Walvis Ridge and all along in the south. But yeah, as I said, they have to be in the crustal domain, these conductors, and do not belong to the sediments. And then there's a second important cluster, this crew D right here, which is the highest densities and also very high resistivities. And that correlates with that prominent resistor R that we saw earlier, all along and below Walvis Ridge in the middle and lower crust. And mostly the other clusters are kind of intermediate in the middle and with larger separations, larger spreading of the parameters. And then to the last domain, the mantle domain. Again, here the criteria indicated 4 different clusters, and I'll also focus on the most important interpretations. So the first one is a rather lower resistivity, of about 100 to 500 ohms, but high density cluster man B, this light pink, and that is exclusively located south of Walvis Ridge, right here in that domain. And the second important one is this big dark red cluster here, which is very high resistivity above 500 ohms and also high density. And again, that matches with the resistor R, so it's located everywhere below Walvis Ridge and all along the ridge. And then one last cluster that I want to point out here is this orange cluster man A, which is kind of widespread in the parameter plots. And in the model plots, you can see that it kind of summarizes the model areas that we don't really trust. So this artifact here, this deep artifact, and then there's also an area here at the very outer end of the model where we're not sure that we actually still have the resolution. So this cluster kind of summarizes outliers. Now, finally, we get to my favorite part where we can actually ascribe the defined clusters to lithology. And to do that, we will go along the margin from south to north, following the successive opening of the South Atlantic. And then we'll always, so I'll start with the transitional crust south of Walvis Ridge, and in these domains, I will always go from top to bottom through the interpretations. In the south of Walvis Ridge, the sediments are all exclusively associated with this cluster ZA, which is the low resistivity, low density cluster. So we interpret that to image thick and coarse and clastic sediments, which are probably of terrigenous origin and that have been transported along the margin, forming deep sedimentary basins. And then in the second domain, in the crust south of Walvis Ridge and that upper crust, we have this very low resistivity clusters of crew A, which is almost the same range as its sediments, but the constraints and the tests indicated that they need to be deeper than the imaged sediments. So our interpretation here is that they summarize alternating layers of basalt flows and sediments or weathered basalt flows. For that, I want to show you a quick insert where I have some resistivity cross sections through the model along these 3 profiles with overlaying of seismic line drawings. And these are seismic profiles from Bilachenko et al. And they have image these SDRs, these seaward dipping reflectors, which are a typical feature in volcanic passive margins. And they are interpreted to be these massive packages of interlayered volcanic flows and sediments. And as you can see on this right-hand image, they coincide nicely with our conductors. So we think that these interlayer packages actually contribute to our upper crust layer conductors. And then the crust and mantle below these are kind of in the median resistivity and median density ranges. So the interpretation there would be that the crust there is mostly a normal volcanic passive margin crust. That means it's an intruded igneous crust because the rifted margin makes room for magmatic intrusions, dikes, and sills, which are eventually also the feeders for these surface flows. And I call this normal because it stands out from the crust that we see further north below Walvis Ridge. So that is the transitional crust along Walvis Ridge, which is in contrast to that. So here we look now at the coast perpendicular profile. And again, start with the top, the sediments. And here, as I said already, close to the coast, we have again this cluster ZA, the low resistivity, low density cluster. So that's again standing for these thick cores and terrigenous sediments in deeper basins. And then if we go further offshore, we have a transition to higher resistivities and higher densities. And we think that this correlates to a transition to more fine and marine and possibly biogenic sediments as we get closer to a marine depositional environment. Then if we go a little bit deeper to the crust below Walvis Ridge in the very east, so close to shore, we have again some of these yellow points of the very low resistivity cluster crew A. So this might also be an indicator for these interlayered volcanics and sediments. But then as we get closer to the center of the ridge, this fades away. And we believe that indicates an increase of magmatic activity. So there's actually less interlayering and more massive basalt flows at the top. And also in the middle and lower crust, all of the model cells are attributed to this high resistivity, high density cluster crew D. So we also say this is now the massively underplated and intruded igneous crust, which correlates with an increase with magmatic input above the hotspot embankment, which also actually built Walvis Ridge. The same thing basically accounts for the mantle below the ridge. It's all of the model cells there belong to the high resistivity, high density cluster man D. We believe that this shows a depletion of the upper mantle because we have the remnants of the massive volcanism that was feeding the upper crust and the surface flows, and what stays back in the mantle is depleted of volatiles and conductive material because they were all extracted in the surface melts. So as a last domain, we go north of Walvis Ridge and look at the oceanic crust there. And yeah, our interpretations there are less confined because we don't have as much data, and the model is strongly influenced by this artifact due to the drastic change in crustal thickness and in bathymetry. So we are generally more careful with our interpretations. But the things that I do want to point out, that it seems like mostly the sediments here belong to this more fine marine and biogenic cluster set B. In the crust, we see that the clusters there are also mostly these intermediary resistivity and density clusters, so it goes up to 400 ohm meters, and median densities between 2.8 and 2.9. And but the crust is very thin there. We know that from seismic observations. So these clusters also show up a lot shallower compared to the southern part. And we think that this matches the observations of basically just a normal oceanic crust north of Walvis Ridge. And then lastly, in the mantle, as I pointed out, you see a lot of these orange cluster dots where we think they mostly summarize cluster outliers. And then the other points here that you see attributed to cluster man D, they're all transparent, so they all have a lower probability. And in the end, we decided to not really interpret the mantle here north of Walvis Ridge. So just a brief summary and a glimpse in what we make of all of this. For the cross-gradient coupled joint inversion, we found that the coupling of the MT inversion with a fixed structural model helped to partially suppress this vertical artifact that we see coinciding with the fracture zone. And it also emphasized the need for these upper crustal conductors because the constraint could not get rid of them. And it also emphasized the need for the high mantle resistivities below the Moho. So we don't actually have an electric Moho there. And the joint data inversion of gravity and MT data did not really alter the resistivity model itself, but it provided us with a matching density model, or matching density values, and that gave us the opportunity to perform the parameter analysis. So that it still proved very beneficial as a joint inversion, and these parameter correlations may also be used as a starting point for future studies with parameter guided coupling. And the implications for the geological interpretations. So what's new from these interpretations? The first thing that I really liked is that we had these upper crustal conductors, and we were first not really sure what to make out of these, but then we could link them with the seismically detected seaward dipping reflectors. That was nice. And then the main interpretation is probably the distinct difference between the crustal structure south of Walvis Ridge and actually along Walvis Ridge. And we link that to a southern domain, which is mostly rift driven. That means it can kind of be seen as a standard volcanic passive margin. And then along the Walvis Ridge, we have this very strong plume influence where magmatic input drastically increased, and that also led to very high resistivity, high velocity, high density above the hotspot or plume impingement. And that's it. Thank you very much.
Thank you very much, Gesa, for this interesting presentation. I forgot to say in the beginning, but Alan put something in the chat, and I think most of you know the drill by now. There is a dedicated Q&A window next to the chat, and please put all your questions in there. I will then read them out, so they're on the YouTube recording, and then Gesa can answer. And during the talk, there was already a first question, so we'll start with that one, and please feel free to add other ones. So Jeffrey D. Schaffner asks, you noted that you had a good correlation for the graph resistivity for the outer seaward dipping reflector trend in the seismic data. But from the line drawing, it looked like you had very similar SDR, seaward dipping reflector type geometries inboard. Could you expand on why you think that there's a change in the geophysical results for the outboard versus inboard SDRs on slide 30? Now,
back to slide 30.
Yes, maybe you know this term, because to me, inboard, outboard
Yeah, I think I
you know what you saw.
Jeffrey
Okay,
means.
then
Let me
then
just
I'll let you.
share the screen again.
Otherwise, we might.
So usually, I think what he refers to is that in the seismic sections, there is usually an inner SDR package and an outer SDR package. And that's, well, here, for example, we see that they're kind of two different packages. I hope that's what he means. And well, my explanation could be that these outer SDR package, I think, are usually then really when we have the interaction, they develop when we have a strong interaction with water. So that means that the volcanism gets a bit more explosive. And that means that we have a lot of pore space that could now in the today environment be filled up with water and then lead to a stronger conductor. Maybe.
Yes, and I think that's what he was asking. Now, Alan is telling me he cannot put a question in Q&A as a host, but Alan, you can talk.
Yeah, I can. Wonderful talk, Gesa. Just going back to your model. It looks to me like your MT models were very vertical in structure.
Oh wait. Yes. This
yeah,
one.
yeah. And I just wondered about whether you could have increased the horizontal smoothness to try and see if you can get models that are not as vertically striped, and also whether the boundaries, the Moho, those boundaries that we know from seismics, Moho and such, whether you could allow discontinuities across them that are not penalized.
So as for the striping, I mean, I didn't try this. It maybe would be worth a try. What we did test here is if we could basically remove this resistor at a certain depth and see if they could still fit the data if we only had the high resistivities up to a certain depth. And whenever we tried this, we could not fit the data. So these tests really showed that we need high resistivities basically all the way through our model here. As for this vertical conductor, I said that, and yeah, the model tests also proved that we don't need this. So we could basically remove this here and just have a conductor in the upper crust, and we could still fit the data properly. So yeah, this is surely an artifact. The resistors, I think we kind of need them.
Yeah, I agree.
Second question was, yeah, you said, I'm not sure I understood this. What was the second question?
Whether the boundaries that you know exist from seismics, the Moho boundary and sediment boundaries, whether you could put those in as unpenalized boundaries so that you can have sharp changes across them that don't add to the roughness.
Okay, yeah.
That's maybe a question for Max, actually.
If I may.
Yeah, go ahead.
Yeah, so technically it's no problem, both things. Yes, we can steer the regularization in the code in all three directions separately, and we can put in the tear zones. I think, well, there are a couple of things. First of all, of course, already with the balance between the joint inversion and the different data fits and so on, there's a lot going on there. So that you have yet another thing that you need to sort of watch out for. And I think one of our questions together, yes, Gesa, was also how much we can do of that with this model constraint, because in a way it serves as a similar thing because it contains some of those boundaries. I don't know if you want to add something to those thoughts.
Well, it's just basically what these model tests earlier already proved it. It seemed like we don't really have an electric Moho, so it feels like why would we want to introduce one?
And that as well, yes. I mean that's a good point as well. And yeah, I mean there are those things, or more tests, more things you can do as always. Yeah. Ian Ferguson has a question. Hi Gesa, nice presentation. How might time evolution of the lithospheric astenospheric boundary after the initial margin formation affect the isostatic correction used, which was based on only compensation at the Moho?
I am not sure the time evolution of the lithospheric astenospheric boundary. So that would mean in comparison to how it was during breakup, I assume. But the corrections that we performed now were all considering present day crustal structure. So
yeah, and I think sort of maybe the hint is, and Ian, if you want to sort of clarify a bit, but I'm guessing it's also about asking sort of where did we assume the compensation is? Where did we assume that things were in isostatic equilibrium?
Okay, yeah. So I mean, there we can actually look maybe at this model by Maestrenko, because they have the lithospheric astenosphere boundary in their model, and yes, of course, there is some variation, but there is not this very drastic contrast between continent and ocean, which we believed is responsible for the strong contrast in the Bouguer anomaly. So I think that's why we chose the Moho basically as a compensation depth, because yeah, we thought this is the strongest influence there from continental crust to oceanic crust.
Yes, and I think, okay, maybe thinking about it now, yes, I mean, there's this concept of isostatically compensated Moho, and then the sort of the residual of that is like if you want to have things like dynamic topography, but we were not really after that. Yes, it was more like a procedure to bring out features in the gravity data. Yes, not necessarily use that residual to as a way to directly analyze the state of the lithosphere. Okay, are there any, so Ian seems to be happy with that answer, and are there any more questions? I mean, I've been heavily involved in this work, so for me it's a bit would be a bit strange to ask, well, a little bit artificial to ask any questions, but maybe, okay, I'll take this opportunity while we're waiting a couple of minutes to ask you, so where do you think this could go next? Or is this now sort of done and dusted?
Well, I said
you are done with it.
I said in the end that I'm done with it. I feel a little bit done with it now, at least. But well, I did say in the end that we use this cross gradient to get some parameter relationship. So I feel there could be an initial first guess, and maybe we could potentially use them to actually derive a parameter-based joint inversion, because why we chose to use the cross gradients was because it's such a large area and we didn't really know the parameter relationships in that area. And now we have at least a first guess. So maybe that could be improved further and then used in.
So something like the cluster centers, or to sort of pull things towards these cluster centers. Yes. Okay. While we were talking, Oskun Kamil Sahin wants to know about the resolution of the EM method. I think it's sort of an explanation of an assessment of the resolution in general.
Yeah. So what I can say to that here is that we did. I did say that we used some 3D. No, this is not the image that I was looking for. We used 3D inversion, although the data was acquired along 2D profiles. So we did some tests there on where our resolution in this 3D model is. And the tests usually showed that we have a good resolution up to about 20, 30 meters away from the stations. And then if we look below the station, so looking at the depth resolution of this model in these MT methods, the passive electromagnetic methods that I presented here, we also are usually just looking at these very large scale anomalies. So if we would, for example, I was talking about these seaward dipping reflectors, which are actually interlayers of conductive and resistive structures. And we only see them here as some big, massive conductors. And if you would want to actually resolve these finer layers, you would probably need a lot better resolution, which the MT method doesn't offer here, especially not in the marine environment.
Yes, and maybe just a final sort of additional clarification. I think you said this it's depth dependent, right? So the shallow, and you can see this in the model, there's the shallow parts of the model have a bit more structure, and then it becomes a bit blurrier at depth because we're sensing bigger volumes.
Mm-hmm.
Well, there's what it always happens. I decide, okay, that's it, and something else comes in. I suppose it takes some time to type. Questions? No, Jeffrey Schaffner says, sorry, no, not at all. We're happy for any questions. So do you have, again, Jeffrey Schaffner, do you have well or outcrop evidence for the interbedded nature of the SDR being conductive and resistive? I suppose that's about what you just said.
Well, we don't have them here at the Namibian margin, but there are quite some drill holes from the Norwegian margin, which is also a volcanic passive margin. And they were able to drill in the seaward dipping reflectors, and they did see this. Actually, they see it in the seismic velocity, but also there is a paper. I don't know. I cannot tell you who it's by right now, but they actually always see this kind of periodic structure of decreasing and increasing resistivity with these interlayering of the flows. So yes, there is some well evidence, basically, just not from this margin directly.
Yes, and then Diloro Fitlo, I hope I pronounced this correctly, wants to know about the computing power, I suppose the computing requirements of these joint inversions. So how difficult?
Do you want to answer this maybe? Since it's
you can share your experience, and then I can add a bit more, because you ran these. Yes, I never actually ran those.
Yeah, this was not done on my personal computer. I had to perform this on a larger cluster at the university. So I think it does need quite a lot of computing power, and it also needs quite some time. So for one of these large scale models to go through all the inversions usually took about 3 to 4 weeks, I would say, to go from the starting model to the final results. And then the more specific technical things are maybe more for Max.
Yeah, I mean, obviously it varies. I think there are two factors here. MT, especially with the land sea, makes it quite slow. So I think if it was just a land survey, for example, it would be easier. The conductive sea and the high contrast increases the computing time quite considerably. And yeah, the joint inversion, what I see with sort of many of these joint inversions, they take more iterations than a single inversion typically to reach the same RMS. And that is related to the nonlinearity of, well, in this case, the cross gradient, but also a lot of the other coupling constraints we're using are quite nonlinear. So you need to run them for longer, and that just adds to the computational complexity. But for smaller models, I mean, I now run land MT gravity joint inversions on a standard, slightly bigger desktop, not quite even a workstation, in reasonable amounts of time, say, meaning a few days. But yes, it does take some time. And okay, now I'll be fast that nobody can ask any more questions, but Alan reminded me to tell you that in a few hours, this video should also be available on YouTube. So if you want to rewatch something or actually look what else is there, go to the YouTube channel and have a look. And I also want to remind you that we're still looking for speakers in 2 weeks and 4 weeks, if I remember correctly from the introduction. So get in touch if you're interested. And well, hope to see you all next week for the next talk, and have a good day. And thank you, Gesa.
Thank you all for coming.